So this is junk work with Omar Fauzi and Anthony Leverrier. And we've studied the so-called quantum expander codes, and we proved that they have nice property for fault tolerance and also for single-shot error correction. So first let me give the context. So we were interested in fault tolerance. So we start with the following fact. Quantum information is fragile, meaning that in an experimental point of view, we are not able to store or to process the information without noise. So the natural question is whether it is possible to build a quantum computer using only noisy gates. And so the answer to this question is yes. It has been given in 1996 with the threshold theorem. So what has been proved is that if you start with a theoretical circuit C that you would like to implement, and that you only can create quantum gates with noise. So you suppose that you can create quantum gates with noise whose noise is below some threshold, and it's important to understand that this threshold is a universal constant in the nature. So if you are able to construct such gates, then given the circuit C, you can create a new circuit C prime, which will first compute the same function than the circuit C, but which will also work when the gates are noisy. And so if we fix some probability epsilon for the circuit to work, we can get this probability of failure. Okay, so let me explain how we can do fault tolerance with the concatenated Steane code. So I will denote by phi the following transformation of a circuit. Each time you have a qubit on your circuit, you replace it with 7 qubits. And for example, if you have the state 0 in your circuit, you replace it by this logical 0, which is this 7-qubit state. If in your circuit you have a ket 1, then you replace it with the logical 1, which is this other 7-qubit state. And then each gate in your circuit is replaced by the corresponding logical gate plus a step of error correction. So for example, for the Steane code, if in your original circuit you have an Hadamard, you replace it by the logical Hadamard, which turns out to be just a tensor product of Hadamards. And this logical gate will act as we expect that it acts. Okay, so with this small drawing, so we start with a circuit with an Hadamard, and we replace it. We replace the qubit with 7 qubits, and the Hadamard with the logical Hadamard plus error correction. So why is it interesting to do that? So first, if you have no errors on your gates, the circuit will act as we expect. So if I have the logical 0 as input, the output will be ket 0 plus ket 1. But the interesting fact is that if I have some error in my circuit, for example, here one gate is faulty, then just after this logical Hadamard, my state is not the right one. Some error has been applied on it. But since I do an error correction step just after, I have the good state as output. And just for the remark, the Steane code can correct only one error, meaning that if in my logical gate I have 2 errors, then at the end I don't get the right output. Okay, so now suppose I have gates, and each gate fails with probability p. I start with my circuit C with m qubits, and I will denote by size of C the number of gates. Then the probability to get the wrong output can be upper bounded by the probability that at least one gate fails. So it can be upper bounded by p times the size of C. Now if I apply once my function phi to the circuit, the number of qubits will be multiplied by 7, the number of gates will be multiplied by some constant. And the nice point is that if I have one error in my circuit, it will be corrected by the error correction step. So to get the wrong output, I need to have two errors, meaning that the probability to get the wrong output is upper bounded by a constant times p squared. And we see that if we take p to be smaller than c, then the probability to get the wrong output decreases compared to the original circuit. And so we can iterate the process. So if we do this k times, then the number of qubits and the number of gates grows exponentially. But the nice feature is that the probability to get the wrong outputs decreases doubly exponentially. So now, if we fix some target probability epsilon, we will need to take k equal log of size of c divided by epsilon to get this epsilon. And so the number of qubits and the number of gates will be multiplied by a polylogarithmic factor. And this work, we are particularly interested in the space overhead, meaning that we are interested in the number of qubits in the final circuit. So the space overhead is defined as the number of qubits in the fault-tolerant circuit divided by the number of qubits in the original circuit. And in this case, we see that we have a polylogarithmic overhead in space and also in time. So the number of gates also is also multiplied by a polylogarithmic factor. OK, so there have been many works to try to reduce the overhead. You have a review by Campbell, Terral, and Villo. And mainly, people study what is called magic state distillation. So let me explain you what it is. So we have this trick called gate teleportation. So suppose that you have some state phi, and you would like to apply a unitary U to this state. Then you can do this, this circuit, and if in the input you have this state phi, as output you get the state that you wanted. But what is nice with this circuit is that you never apply directly the unitary U to your state. Instead, the problem reduces to create this state. And OK, so you need to apply the unitary U, but you apply it to a fixed state. So this is much more simple. Yeah, and so the problem is, so we reduce the problem to create this state encoded in the error correcting code. And there have been extensive work on this, and this is called magic state distillation. OK, so here are some papers about that. But the point is that even with these techniques, people generally use surface codes, which are zero rate, and meaning that we need to concatenate the code, and we still have the polylogarithmic space overhead. OK, so when we use zero rate codes, the way it works, each qubit is replaced by a polylogarithmic number of qubits. And so this is clearly not the most efficient. What would be much more efficient would be to use constant rate codes, meaning that we encode k qubits using eta k qubits, where eta is some constant. And so this is, I guess, quite natural to try to do that, but some problem arrive. And so in 2013, Gottesman used this idea to prove that it is possible to do fault-tolerant quantum computation with constant space overhead. And so what he proved is that if you start with a circuit with m qubits, then you can create a fault-tolerant circuit with a linear number of qubits. And so the idea is the following. So as I said, you encode k qubits into eta k qubits. And for example, if I apply this Adama on the qubit number I, I will need to first do the logical corresponding Adama on my qubits, and then do an error correction step. The problem is that in his paper, Gottesman showed how to perform this logical Adama, but for the error correction step, it was not really clear how to do it. Okay, so just quickly, for the logical gates, we use the gate teleportation trick. And then we need to create the states. And the way Gottesman do that is to use concatenated code. So he used the techniques I showed you in the previous slide to create an arbitrary state. Yeah, so for the error correction step, it's a bit more complicated, and you need so you need an error correcting code with many properties. So here are the properties. So first, as I told you, we need a constant rate error correcting code. Second, we ask that the code is low density parity check. This means that the parity check matrix of my code is sparse. And so we need that because we don't want the error to propagate when we measure the generators. Also, we want the code to be efficient against constant rate random errors, meaning that each gate in my circuit has some probability to be in error. Also, the probability to fail. Sorry. Okay, so this is not okay. So the probability that the decoding fails is decreases as exponential of minus alpha square root of n. So this is not 1 minus. This is just the exponential. So what we want is that the probability to have a failure in the decoding goes to 0 faster than any polynomial. Also, since we implement the measurement of the generator with noisy gates, we also want that the decoder works when the syndrome measurement is noisy. And finally, a property which could be a bit surprising is that we need constant depth classical computation. Why do we need that? Because when we measure the generators, first we measure the generators and then we apply the correction. And so between these two steps, you have classical computation, but you cannot wait for knowing how to correct your code. So that's why we ask to have constant depth classical computation. And so yeah, the natural question is, do such codes exist? And in this work, we prove that such code exists. And in particular, we proved that the quantum expander code decoded using the small set flip decoder have these 6 properties. And moreover, we showed something very interesting. So I did not emphasize it in the title, but this code have also the single shot property, meaning that when we want to correct the error, we need to measure the generator only once. And so that's a really interesting property. And so this work follows these 2 works about quantum expander code. Okay, so the content of my talk will be the following. So first, I will define what are the classical and quantum error correction. Then I will define the quantum expander code. Then this third part is a bit technical. I will try to explain you how we proved our results. And then at the end, I will summarize how Daniel Gottesman did fault-tolerant quantum computation. Okay, so first classical and quantum error correction. A classical error correcting code can be defined as a k-dimensional subspace of f2 to the n. And for this work, we are interested in the representation using a parity check matrix and factor graph. So a parity check matrix is just a matrix such that the code is equal to the kernel of this matrix. And we represent the matrix using a factor graph. So a factor graph is just a bipartite graph. The rows of the parity check matrix are represented by the checks. The columns of the parity check matrix are represented by the bits. And you have an edge between a bit and a check when you have a 1 in the corresponding rows and columns. OK, so this was the classical error correcting code. We would like to study the quantum error correcting code. So the setting we use are the stabilizer codes. So stabilizer code is defined as the set of states, of quantum states, which are fixed by Pauli operators that we call the generators. Yeah, so in this talk, generally I will use n for the number of logical qubits of my code and k for the what did I say? N the number of physical qubits and k the number of logical qubits. So these are the stabilizer code, and so we asked that our code are constant rate, meaning that k grows linearly with n. More particularly, we are interested in CSS codes, which are a particular case where the generators are either a product of identity and X poly matrices or product of identity and Z poly matrices. And what is nice with this CSS construction is that you can define CSS code using 2 classical error correcting code. So you can use all the work that has been done in classical error correction to study these codes. And yeah, we asked that the code are LDPC, meaning that the parity check matrix of my 2 classical codes are sparse. Are sparse, yeah. OK. So for example, the Steane code that I used to do to show you how to do fault tolerance in the introduction is a CSS code. And it's the CSS code when you choose CX and CZ to be 2 classical Hamming codes. And so since you have this standard graph representation for the classical Hamming code, for a CSS code, you also have a standard graph representation. And that will be very important for defining the quantum expander code. So the standard graph of a quantum code is just the 2 standard graph of the 2 classical error correcting codes. OK, what we studied is a decoding algorithm for the quantum code. So a decoding algorithm is works in the following way. So first, we generate qubit error and syndrome error. So I will denote by E subscript qubit and E subscript syndrome these errors. The second step is to measure the generators of the code. This gives us a syndrome. And since we are in the case where the measurements are noisy, what we get is the syndrome of the qubit error, XOR the error on the syndrome. Then what we study is this algorithm. So the decoder is just an algorithm which takes as input this syndrome and tries to get what was the error on the qubits. And this is what we will study in what follows. And finally, we apply the guess correction in order to correct the error. OK, so what we asked is that we have constant rate random errors, meaning that these errors are constant rate. We also ask constant depth classical computation, meaning that this algorithm has to work in constant time. Also, we ask that the probability of decoding failure, OK, again. Yeah, again, it's not 1 minus, it is exponential of minus alpha times square root of n. So we ask that the probability of failure goes to 0 very fast. and that's all. Okay. So let's take a look at the non-construction of quantum LDPC codes. So first, I guess most of you know the toric code. So this code is really nice because the minimal distance is good, and the probability of decoding failure is really good also. But the problem with this code is that it has finite dimension. So if you want to use it to do fault tolerance, you need to concatenate it, and you get the polylogarithmic overhead. Then there exists also hyperbolic 2D codes, which are defined as the tessellation of hyperbolic 2D manifolds. So here, the dimension grows linearly with n, so they have constant rate. That's interesting. But since the minimal distance only grows like a logarithmic in the number of physical qubits, the probability of decoding failure decreases as a polynomial, and that's not enough for what we want to do. Then, if we increase the dimension, we can create hyperbolic 4-dimensional codes. The dimension also grows linearly, and the minimal distance grows like a power of n. So it's possible that this code could be used for a fault-tolerant scheme, but unfortunately, Hastings only proved that the probability of decoding failure decreases as a polynomial. And then, so we have the code for this talk. So the hypergraph product codes have a linear dimension and a great minimal distance, but in full generality, we don't know how to decode them. So if we take a particular case of hypergraph product codes that are called the expander codes, we are able to design an efficient decoder, and the probability of decoding failure will be small enough. Okay, so let's define now the quantum expander codes. Okay, so before defining the expander codes, we need the notion of hypergraph product code. So this has been introduced by Tillich and Zémor in 2009, and we want to create a quantum code using two classical error correcting codes. So be careful. These two codes are not the two codes for the CSS construction. So we start with two classical error correcting code, and we do the product. So just for simplicity, I will call this code the red code and this code the blue code. Okay, so the blue code is horizontally, the red code is vertically, and what we do is that we define the product in the following way. So we define these 4 rectangles, and the qubits are placed on this top left rectangle and on this bottom right rectangle. The Z-type generators are in this top right rectangle, and the X-type generators are on this bottom left rectangle. So this defines the qubits and the generators, and now we need to define what is the incidence relation between these qubits and generators. So the idea is that each column here is a copy. Each column is a copy of the red Tanner graph. So for example, if I take this column or this column, here I see that I have an edge between this bit and this check node, so I have an edge between this qubit and this generator. Similarly for this column, and similarly if I take this edge here, I have an edge here and here. So you have copies of the red Tanner graph in the columns, and you also have a copy of the blue Tanner graph in each row. Okay, so to summarize, you have your qubits here and here, the generators here and here. Here you have the blue code edges, the red code edges, and the red code edges. So this defines the Tanner graph of the quantum code. And for example, if you forget about the X-type generators, then you get the Tanner graph of the classical code CX used for the CSS construction. And if you forget about these Z-type generators, you get the Tanner graph of the code CZ, which is used to correct the Z-type errors. Okay. So this construction is nice because first, if you take the red and the blue codes to be the repetition code, what you get is the toric code. Second, if you take good classical code, so good classical code means that the dimension grows linearly and the minimal distance grows linearly, then what you get is a quantum code with a number of logical qubits linear and the number of physical qubits, and the minimal distance of the code grows like square root of n. One issue is that if you start from a classical code with an efficient decoder, then we don't know how to design an efficient decoder for the quantum code. And so that's a problem. And what we proved in this paper is that if you take the red and the blue code to be classical expander codes, then you get what we call the quantum expander code, and it is possible to design an efficient decoding algorithm for them. Okay, so yeah, now I need to define the classical expander codes. They have been introduced by Sipser and Spielman in 1996. And the idea is the following. So first, okay, we represent it using the Tanner graph. I will denote by gamma of E the neighborhood of a set of bits. And we are interested in Tanner graph with left degree D. So of course, if you always have this in this upper bound, okay? The number of neighbors of E is upper bounded by D times E because we have a D regular graph. And what did Sipser and Spielman said that maybe we could ask this upper bound to be tight up to a small factor. Okay, so let's define an expander graph, a graph such that if the error is small enough, then the neighborhood of E is close to this upper bound. So of course you need to prove that such graph exists, but using probabilistic arguments, you can show that such graph exists. And if you want delta to be small, you can increase the degree of your graph, and you will get delta as small as you want. Okay, and what they proved is that if you consider this classical error correcting code, you can decode it using the bit flip algorithm. And the bit flip algorithm is maybe the simplest algorithm you can think about. So the idea is to go through all the bits, and you find a bit such that flipping this bit decreases the syndrome weight. And so, okay, at each step, what we do is that we find a bit, we flip it, and we repeat step 1 while we are able to decrease the syndrome weight. Okay, and so what they proved is that if the error is small enough, then the bit flip corrects this error. And let me give the proof. We start from some error E, and I will denote by E subscript final the final error. So suppose this error is not empty. Then what we know? We know that the decoder stops on this error, meaning that there is no bit such that flipping this bit decreases the syndrome weight. So this means that we have this inequality here. And if we look at this inequality, this means that the neighborhood of the error sees the neighborhood of the error seen as a multiset has many intersections with itself. And so if it has many intersections, this means that the size of the neighborhood can be upper bounded by 3/4. So 3/4, we get 3/4 with the calculus, but we get this upper bound. And since by definition, an expander graph satisfies this property, we cannot have this inequality, and so we get a contradiction, and the final error cannot be empty. Okay, so now let's define the quantum expander codes. So they have been defined in 2015. So a quantum expander code is just an hypergraph product where the two classical codes are classical expander codes. But the problem is that if you try to do the same algorithm, it doesn't work. So there are counterexamples which shows that if you try to flip 1 qubit at each step, then you can be blocked with this algorithm. So the idea to do better is to try to flip several qubits at each step. And so the algorithm is called the small set flip algorithm. And the idea is to find a subset of a next type generator such that flipping this subset will decrease the syndrome weight. OK, so first we generate an error, E subscript qubit and a syndrome error. So OK, the input of the decoder is the noisy syndrome associated to these two errors. And the decoder principle is the following. We find a set F such that F is a subset of an X-type generators, and flipping F decreases the syndrome weight. And we repeat that while such F exists. And in what follows, I will call a subset of an X-type generator a small set, and I will call a valid small set a small set such that if I flip this small set, it decreases the syndrome weight. OK. OK, so this third part is a bit technical. I will try to explain you how our result works. So again, the qubits, I have an error on qubit, an error on syndrome, and I will denote by E subscript final the reduced qubit error after applying the small set flip decoder. And the first remark is that since we are using LDPC codes, we cannot ask that the final error is empty with high probability. And the reason for that is that you cannot distinguish between a single qubit error and a constant weight error on the syndrome. So what we will ask is that the final error is local stochastic. So let's define what is a local stochastic error. So it's defined using this formula. So this model is used in fault tolerance, but if you don't know about it, you can just think that it is an IID error. So you have two probability of error, and each qubit has probability p qubits to be in error, and each check has probability p syndrome to be in error. Okay, and the main theorem that we proved is that if the probability of error in our qubit is smaller than some threshold, and the probability of error in the syndrome is smaller than another threshold, and if we start with an error which is local stochastic with these parameters, then with high probability, the final error will be a local stochastic with parameter p0 divided by 2. So this p0 divided by 2 could be a bit surprising first. The reason we asked that is that OK, so when we apply our error correcting step, we get an error with probability p0 divided by 2. Then we apply some logical gates. We increase the probability of error. Then we apply an error correction step. We go to p0 divided by 2. Then we increase it. And so the idea is that we don't want to erase all the errors. What we want to do is to keep the error below the threshold. So it's enough to ask for this property. OK. So the proof sketch, one of the key lemma that we proved is for the analysis of small size errors. So what we proved is that if the errors on the qubit is smaller than the minimal distance, then, with probability 1, the final error, the size of the final error, can be upper bounded by a constant times the size of the syndrome error. Then using a percolation-based argument, similar to the one used by Kovalev and Priyatko, we showed that if the error is local stochastic, then with high probability, the size of the final error can be upper bounded by this. And then using simple probabilistic arguments, we showed that if the initial error is local stochastic, then the final error is local stochastic with high probability. So in what follows, I will not talk about percolation on graph. I will not talk about this part. I will focus on this key lemma, and I will try to show you how to prove that. Just a quick remark. For this key lemma, we need the expansion property, but then once we have this key lemma, we only need to have LDPC code to be able to conclude here. So that's interesting maybe for a generalization of this result. Okay, so again, the key lemma is the following. If the qubit error is smaller than the minimal distance, then the final error can be upper bounded by a linear function of the syndrome error. And the proof trick is to analyze the qubit error using the noiseless syndrome case. In the previous analysis, what was done is that in the noiseless case, it was proved that it is possible to find one valid small set flip per round. And the problem with that is that when we have measurement errors, if the error intersects the syndrome of this small set, we do not know if flipping this set will still decrease the syndrome weight. And so the small set F might not be valid anymore. Okay, and so in this work, what we did is that we proved that in the noiseless case, we find several valid small sets at each step. And so when we have noisy syndrome measurement, if the noise on the syndrome is small enough, then we can find one of these small sets such that which is not corrupted by this syndrome error. Okay, so the proof sketch is in two parts. First, we analyze the case where the syndrome error is empty, and then the case where it is not empty. So when the syndrome error is empty, we define F1 to be the set of small sets which are flipped by the decoder at step 1, 2, 3, etc. Then we define F2, all the small sets in F1 such that this small set was valid at step 1. Okay. And then we analyze the case where the syndrome is noisy, and we define F3, the set of small sets which are not corrupted by the syndrome error. And it turns out that any set in F3 is a valid small set at step 1 for the decoder. And what we will prove is that all this set F have size which is linear in the size of the syndrome. Okay, so first let's construct F1. So we are in the case where the syndrome is noisy. So the key property of expander codes is the soundness property. This is really important. So it says that if the error on the qubit is smaller than the minimal distance, then the size of the syndrome is linear in the size of the error. And in fact, the expander codes are the codes which are the best for the soundness property. What do I mean by the best? If we look at the classical case, since we use deregular graph, we can upper bound the size of the syndrome by d times the size of the error. And the expander graph satisfies that this upper bound. Okay, so for the expander graph, this upper bound is tight up to a factor 1 minus epsilon. And so in the quantum case, they also are the best for soundness, but the way to express it is a bit different. So let me explain you how to do that. So if I take an error which is smaller than the minimal distance, then using the small set flip algorithm, you can write this error as a sum of small sets. And by definition of the syndrome of the error is equal to the sum of the syndrome of the small sets. So now we define our set F1, which is all the small sets which are flipped at step 1, 2, 3, etc. And then, so by a simple union bound, since we have this property here, the size of the syndrome is upper bounded by the sum of the size of the syndrome of the small sets. And so this upper bound is tight for the expander code up to a 1 minus epsilon factor. OK. So these two properties have been proved in the previous slide. So OK. Now, so we are still in the case where the syndrome is noisy. Let's take a check node in the syndrome of the error. By definition, we know that we have this. Okay, we know that we have this. So one check node in this set is at least in one of these sets. Okay, and so we know that if I take a check node here, it will be in one of these sets, and so we have this inclusion. Okay, and then using this inequality here, I know that this quantity is first upper bounded by the size of the syndrome, and using this inclusion, it is upper bounded by the sum of these quantities. Okay? So why do I want to do that? If we look at this inequality here, we have here the sum over the small sets, and here also we have the sum over the small set. So if I take epsilon small enough, so that this quantity is smaller than, let's say, 1/4, then we know that there is a linear number of f, a small set, such that this guy here is greater than this guy divided by 2. OK? Yeah, and so if we have this property, this exactly says that if I flip the small set f, it will decrease the syndrome weight. So this f will be a valid small set at step 1. OK, so we have proved that if we define this set of small sets, then they can be flipped at step 1, and the size is linear in the syndrome size. And now let's define the set F3. So in the case, so this was the analysis of the case where the syndrome is noisy, and now we are interested in the case where the syndrome. Sorry. So this was the case where the syndrome is noiseless, and we are interested in the case where the syndrome is noisy. So let's suppose that we have a non-zero error on the syndrome, but we can upper bound its size by this quantity. Then, since we use LDPC code, it's quite easy to show that the error on the qubit is linear in the size of the syndrome. And since we have this, we know that the syndrome error size is upper bounded by this divided by 2. OK, and then if we define the set F3 as being the small set whose intersection with the syndrome error is empty, then we get, using this inequality, that this set has size linear in the syndrome weight. OK, so what I proved is that if the error on the syndrome is small enough, then we can find a linear number of small sets which can be flipped at step 1 by the decoder. And what does it mean? By contraposition at the end of the decoder, I know that I cannot flip any subset, so this is false. And so what I get is that the qubit, the size of the qubit error is upper bounded by a constant times the size of the syndrome error. And also, another consequence of this is that since at each step we have a linear number of small sets that we can flip, it is possible to parallelize the algorithm. And what is quite surprising is that we can parallelize it to run in constant depth. OK, so that was maybe a bit technical. So now I will explain you how works Gottesman's fault-tolerant scheme. So again, we start from a circuit C with m qubits and size of C locations. And the idea is to encode k qubits into eta k qubits. OK? And the ideal case to do that would be to do only one block, meaning that in my circuit, my m qubits are encoded into eta m qubits. But it turns out that it's an open question to know whether it is possible to do that with a single block. Because for the quantum expander codes, you need to do many blocks and a polylogarithmic number of blocks. And I will try now to explain you why you need to do a polylogarithmic number of blocks. So first, similarly to the case where we use concatenated code, each location in the circuit is replaced by the corresponding logical location plus an error correcting step. So when we want to prepare a state, we do state preparation using concatenated code. When we want to do a logical gate, we use the gate teleportation trick, plus we prepare the state using concatenated code. For the final measurement, we use transversal destructive measurements. And also for error correction, it is sufficient. It should not be optimal, but it is sufficient at least to do a non-fault tolerant error correction. Since we are using LDPC code, the error will not propagate too much, so that's sufficient for this talk at least. OK, so let me explain how to do straight preparation. So I have an NK expander code, and what I would like to prepare is this state phi, which is either the initial state, meaning the logical 0, or this state encoded in the expander code, which will be used to do the gate teleportation trick. And the idea is just to first find a circuit D which is not fault tolerant, but which output is phi, and then to simulate D by D prime, where D prime is a fault tolerant version of D using concatenated codes. And so since we want the probability to get, we want that the probability that one gate fails to be small, so we require that the probability that D prime fails is smaller than this quantity, for example. And so we have a probability target. We know the number of qubits in the original circuit D, and we know the size of the circuit D. And so using the usual fault-tolerant theorem, we know that the number of qubits in the circuit D prime has a polylogarithmic overhead compared to n. And now, using just a small calculation, you can show that if you do a polylogarithmic number of blocks with your expander codes, then the number of qubits will be negligible compared to the number of qubits in the circuit. And so we get a constant space overhead. OK, so let me recap what I showed you in this talk. So we proved for the quantum expander codes that it is possible to perform fault-tolerant quantum computation with constant space overhead. Also, I would like to emphasize this result about single-shot error correction. In my point of view, it's very interesting to get this result. So again, single-shot error correction means that when we measure the generators of the code, we need to measure it only once. Whereas, for example, for the toric code, we need to measure it square root of n times. And also, we've proved that the small set flip decoder can be parallelized to run in constant depth. So for the moment on the archive, we only proved that we can do in a logarithmic number of steps. But yeah, the proof is the same. We just didn't realize that we can do it in a constant number of steps. So we will put it on the archive soon. Also, as a future work, it would be interesting to know what are the links between the soundness property I presented you and the single-shot error correction. In particular, there was a talk on about this on Wednesday, I guess, by Al Campbell. So I guess this is an interesting question. In particular, if we are not interested about single-shot error correction, but single-shot error correction with the small set flip decoder, so a property which is interesting is that if you can decode your code using the small set flip decoder, then this implies that your code has a linear soundness. And the question which is interesting is to know whether if you have a linear soundness, then you can be decoded using the small set flip decoder. Second, yeah, so this small set flip decoder is nice for theoretical analysis. In practice, it's not so good. For example, if we compare with the classical code, the bit flip algorithm is not good compared to the belief propagation algorithm. So it would be very nice to be able to do some kind of a belief propagation algorithm for the hypergraph product codes. So that's not clear how to do that, but it would be very nice to do that. And also, yeah, so the result I presented you is really an asymptotic result. Nothing has been done to reduce the constant, but yeah, it would be interesting to check whether we can get better constant for this construction. And yeah, thank you very much.
Okay, questions for Anton?
So, sorry, I was a little bit confused as to what you actually do for the error correction procedure. So you see some synchrome, you don't know which are the synchrome, the noisy bits, which ones are errors and which ones are really representing them. So what do you actually do then?
Does this work? Hey? Oh. Hey? Yeah. Yeah, so in fact, we do exactly the same than when there is no error syndrome. And it turns out that this works. Because of this soundness property, it works.
Okay, so your analysis, you had some sets where there was no synchrome error and some sets where there was synchrome error, but it looked like you were then saying that most of them didn't have synchrome errors. And the point is that the ones that have synchrome errors, you don't know what happens, but it can't be too bad? Is that the basic argument? Like your F3 was saying that there...
What is important is to prove that if the syndrome error is smaller than something linear in the qubit error, then this will not cause problems. Sure. Is that clear? I don't.
Yeah, yeah. I'm just not quite clear on how you prove that.
Okay.
Can you maybe go back another slide?
Which one?
Back. Yeah, it's here. So, I mean, so this set F3 is the set of things where there's no synchrome error.
Yeah, exactly.
And the question is then what happens to the ones that do have synchrome errors? It's just that
okay.
You might try to correct those, but it might go wrong and you just don't care?
So this argument works for one step of the decoder. So I defined this set F2, which are all the small sets which can be flipped when there is no syndrome error. And now I take a subset of this set, which are the sets which can be flipped even when there is syndrome errors. So the other one cannot be flipped at the first step. But once we have done this step, we do a second step, and maybe they will be flipped after.
Yeah, sorry, but this is the part where I'm confused, because you don't know when you're doing this decoder which ones have synchrome errors and which ones don't have synchrome errors.
Right.
So you're not going to know which ones you're allowed to flip and which ones you're not allowed to flip.
Right. Okay. So again, this is a consequence of the robustness property. The soundness property. To prove that the error can be corrected, it is sufficient to prove that the decoder is not blocked. If you can prove that if the error is small enough, then your decoder is not blocked, then using the fact that you use the small set flip decoder and your code is LDPC, then this implies that you correct any error up to the minimal distance.
Yeah, okay, I'm just trying to get a little bit more understanding of how that happens. So,
yeah.
so what you see is you see a bunch of sets. You say, okay, there's a small set here, a small set here, a small set here. And here, maybe that's fine. There's no synchrome errors and you're doing the right thing. But here, it's wrong. There is a synchrome error. And so what happens there? You try to flip it, but it just can't create too many errors because of the soundness property? Is that just the argument?
Yeah, right. Yeah, so of course sometimes you will flip qubits which are not in errors. But okay, at the end we don't get no error at all. What we get is that the local stochastic parameter has been divided by 2, and that's all what we need. We cannot, and in fact we cannot do better with single shot error correction. We cannot erase all the error because you can.
Yeah, well, you never can, because there could be something in the last step.
Yeah.
Okay, so we have time for 1 or 2 more questions. At the back.
So, what are the prospects for non-additive versions of any of this theory?
Sorry? For?
What is the status of non-additive codes with these sorts of treatments? Because they have other properties. I mean, in the extreme case, you had the Friedman-Levaux thing, and there you had the thing that I don't know what you would call it, holonomic or homomorphic transformations of the code was already universal for quantum computation. I'm not sure how important that is, but in any case, I was wondering whether you are locked into additive codes for this for all of these constructions.
I did not understand the question. Sorry.
Well, see, what you did was all of your codes are additive, and moreover, there's CSS.
Yeah.
The CSS part you can get rid of. You can generalize to other additive codes. But from the beginning, you started with additive constructions that were refinements of linear classical codes. So now there's an analogy that nonlinear classical codes are analogous to non-additive quantum codes. And non-additive quantum codes sometimes have extra properties. So I'm wondering whether restricting the additive codes is really seen as necessary for all of these ideas.
Okay, I don't know about it. I don't know.
Okay, if there are further questions, maybe we can take them into the coffee break. I think there will be an announcement, but let's thank Antoine again.